Hello, everyone. Hello, everyone. Thank you for joining us today. My name is Matt Graham, and I'll be hosting today's event. It'll be around 40 minutes long. If you've got any questions, either during or afterwards, pop them in the Q&A, and we'll answer them at the end. The webinar will also be available to watch on demand afterwards if you want to rewatch it or share it with any of your colleagues. So without further ado, I'll pass over to my colleague, Hemi, who will be leading the webinar today. Hemi, over to you.
Thanks very much, Matt. Thank you all for joining this morning. Today, I'm going to be covering a webinar on new approaches to sample preparation workflows for heavy metal analysis, particularly focusing on microwave digestion. So in today's agenda, I will cover start by covering the analytical workflow for heavy metal analysis, and then cover some of the options for sample preparations for this analytical technique and some considerations that need to be taken into account when choosing an appropriate technique. We'll cover conductive heating digestion, and we'll also cover microwave digestion with a focus on two areas of microwave digestion: rotor-based microwave digestion and single reaction chamber microwave digestion. And we'll also cover some real world examples with these as well. So starting at the beginning, we have the heavy metal analysis, and analytical labs for many years have adopted advanced approaches to this type of analysis. This includes techniques such as inductively coupled plasma optical emission spectroscopy and inductively coupled plasma mass spectrometry, to name a few. This analytical approach provides labs with a route to determining what elements are in their sample at really high sensitivities and low detection limits. Heavy metal analysis offers vital information on sample composition across a range of application areas. This includes application areas such as environmental testing, food and feed testing, pharmaceutical industry, geological and material testing as well, such as battery testing, lithium-ion batteries, and composites, just to name a few. ICP-OES and MS techniques offer increased productivity, improved data quality, and really meet the ever-evolving regulatory and research requirements of the modern lab. A really important step in this analytical workflow is sample preparation. Samples for this type of analytical technique are commonly introduced as liquids, and therefore these systems cannot handle solid samples. These types of samples need to be dissolved into a particle-free solution. This dissolving is typically carried out using an acid or acids, and these are chosen dependent on your sample type. And we refer to this process as digestion. Over the years, sample preparation has evolved from relatively rudimentary open vessel digestions all the way to advanced modern closed vessel digestions. And how you carry out your digestion is a really critical step to ensuring the highest quality data. If you have a poor sample prep approach, you're going to have poor data. As well as thinking about the data side of things, your sample prep approach can really limit your productivity as well, with incomplete digestion leading to poor recoveries, interferences, and unreliable data. Additionally, outdated technology lacks that safety and sustainability that modern labs are striving for. Labs are facing growing demands for faster turnaround, improved accuracy, and lower operational costs. By optimizing your sample preparation workflow, this is a really simple route to improving the overall analytical workflow. So like I mentioned in the intro, The approaches we're going to cover today are conductive heating using hot plates or hot blocks, and then microwave digestion, focusing on rotor-based microwave digestion and single reaction chamber microwave digestion as well. When deciding which approach to sample prep is most suitable to you, there are a number of considerations, which we can see here on the left-hand side. You need to consider your sample type. Is it organic or inorganic? And what potential reactivity that will have when you're digesting it. Additionally, you need to consider your sample weight. The sample amount you're digesting will directly impact the maximum pressure exerted when digested, and the digestion system you're using needs to be able to handle those pressures generated. Loss of pressure can lead to loss of volatiles, generate high amounts of acid released, and sometimes is not compatible with official methods. Additionally, you need to choose appropriate acid chemistry for complete digestion. Let's take organic sample, for example. You would need maybe nitric or aqua regia to digest these types of samples. Or if you had an inorganic sample with lots of silicates, you would need HF to digest these. Ultimately, the goal is to achieve that complete particle-free digestion. And to do this, you need appropriate digestion conditions with the appropriate temperature and pressures, and your system needs to be able to achieve these. As well as achieving this complete digestion and recovery of those target elements, the modern lab is always looking to improve these 4 areas: costs, increased automation and reduced operator time, efficiency, so no sample reprocessing and lower risks of contamination, the quality that you're putting out, so better LOQs and minimizing those interferences, and then of course safety with less exposure to acids and less acid handling for the users. And all of this can be achieved by choosing optimized sample preparation approach, and we'll focus on how these 3 different approaches can support benefiting all these areas. So let's go on to the different digestion approaches, starting with hot plate or hot block, which is a conductive heating digestion. This is a really traditional approach to carrying out digestion, which uses a variety of reaction vessels with a range of sample masses digested. As you can see here on the right-hand side, there are a range of heating surfaces available, which offer batch digestion with flexibility in the number of samples you digest. This approach is probably the most limited in terms of sample preparation approach. It's very time consuming. For most applications, it can take hours, potentially days for complete digestion. However, we do see across the market that there are some applications where this is quite quick for in minutes opposed to hours for complete digestion. But as a process, it is quite labor intensive for users as well, so that needs to be taken into consideration. Digestion is carried out in open vessel systems, and this can potentially lead to things like loss of volatiles and cross-contamination from, say, neighboring samples or the lab environment around them. Being in open vessels, it's quite difficult to control the reaction as well, so there's potential for repeatability issues too. And as you'd imagine, with boiling hot acids in open beakers, there are safety considerations that must be taken into account, and also these must be ran in a fume hood. Being in open vessels, you're working at atmospheric pressures and are limited to the temperatures you can reach, so it's not a suitable technique for those tricky to digest samples as well. So a way to overcome these limitations and improve quality, efficiency, safety, and costs in your digestion workflows is by using microwave digestion. Microwave digestion is a closed vessel approach which is widely recognized as being the most effective technique for digestion of samples because it enables you to reach those much higher temperatures and pressures that you can't reach using hot plates or hot blocks. This increased speed in digestion from hours to minutes really opens up the possibilities of types of samples you can digest. As suggested with closed vessel digestion, the sample is enclosed in a sealed vessel that is made of high quality material to minimize contamination. And this closed vessel system eliminates potential for cross-contamination and loss of volatiles. Additionally, all our microwave systems are fitted with an exhaust system, which means they don't need to be run in a fume hood. They're simply hooked up to your extraction system, which frees up valuable fume hood space in the lab. So in terms of what I'm going to cover on microwave digestion today, there's two approaches. We have rotor-based microwave digestion and single reaction chamber microwave digestion. Rotor-based is the classic approach to microwave digestion with an oven-type cavity fitted with rotors made up of a number of sealed vessels, which range up to 44 positions for simultaneous digestion of batches of same sample types and acid chemistry. Single reaction chamber technology, the digestions take place in simple two-part vials, which contain your sample and your acid, which are then placed into a pressurized PTFE-lined stainless steel reactor. This approach gives labs unmatched performance and productivity, which we'll explore throughout the webinar. For both of these approaches, we have a number of systems available to meet your requirements in the lab, so we will cover those in more detail. Starting with rotor-based systems, we have the brand new models of the ETHOS and the ETHOS Lean. Both these systems offer the same benefits of closed vessel digestion, with the Lean being a more compact system with a smaller scale of throughput. The rotor-based systems are really based on four main pillars. We have really rugged hardware. There's rugged stainless steel cavities, made of rugged stainless steel cavities with corrosion-resistant coatings. Really accurate digestion control through contactless infrared sensors, which offers you really high quality, reliable and reproducible digestions, all while being kept in a safe environment. You can see on the right hand side of the system, they're controlled by a smart user interface. This is really straightforward to operate. You simply select your method, press start, and your digestion begins with your temperature and power monitored in real time during the digestion process. And then finally, one of the most important parts of the rotor-based systems is the advanced digestion rotors. Digestion vessels are really at the core of the microwave system, and our rotors are designed to deliver high performance and safety. And there's three different options across the two models, differing capabilities. So we have the high throughput maxi rotor, which is a 44 position for the ETHOS or a 14 position for the Lean. We then have the high pressure rotors, which is a 15 position for the ETHOS or a 6 position for the Lean. And then finally, we have a nice balance of the two of high throughput and high pressure capabilities with the Maxi high performance rotor, which is either a 24 position for the ETHOS or a 14 for the Lean. So I'm just going to cover those rotors in a bit more detail now. Each rotor is built of high purity PTFE vessels and cover, which ensures broad chemical compatibility with ultra low blanks. This is all the rotors are reinforced with PEAK shields, which are designed to withstand the high pressures that you experience at elevated temperatures when carrying out closed vessel microwave digestion. Another really nice feature of all the rotors is that they incorporate vent and reseal technology. This keeps the vessels completely sealed during the digestion process. Here at Analytics, we can work with you to design a method that will prevent venting from happening, as this sort of technology is designed to act as a safety precaution in the rare event of overpressurization. And venting should be completely avoided when you're working with rotor-based digestion systems. So let's go into each of the rotors in a bit more detail. I'll cover these specifically for the ETHOS system, but you have the options for the lean as well. So we have the Maxi 44 here, which is up to 44 position rotor, which offers maximum productivity for labs processing large sample batches. As mentioned, you have the 44 PTFE vessels up to 100 ml volume, and it really delivers high throughput reliability and has a really nice ease of use with a 3-part twist cap for the vessels. It's kind of suited for easy to digest samples with low reactivity, and we're typically working at digestion temperatures of 180 degrees. The Maxi 44 is really a natural solution for labs that have demand in efficiency in handling large sample batches. You can see a few applications mentioned here, such as food and environmental testing labs. Then moving to the SK rotor, we have the SK15, which is a rotor capable of operating at high temperatures, typically around 220 degrees. And this rotor can handle the pressures generated when you're working at those temperatures with a maximum working pressure of 100 bar. This rotor has a capacity up to 15 PTFE vessels of 100 milliliters again, and its broad working range makes it ideal for virtually any sample matrices, including hard to digest samples such as ceramics, geochemistry, and metal samples, all the way to your reactive samples. So take, for example, petrochemical samples or polymer samples, but also allows you to work with slightly larger sample masses as well. Combining the benefits of those two rotors, we have the Maxi high performance rotor, the Maxi 24 HP, which is a really unique rotor in the microwave digestion field, combining increased pressure limits with that greater capacity than your standard high throughput rotors. The design of this enables increased compatibility with more sample types and weights in a single rotor-based system. You have the ability to digest up to 24 samples simultaneously, and with the Maxi 24, you can increase throughput, generate high quality data, and have more profitable runs, and is really a great choice of rotor for digestion of a diverse range of samples, which I've just highlighted down at the bottom there. So I just wanted to showcase the ETHOS in a real world example, specifically for a food analysis application. So the performance of the ETHOS was evaluated through a recovery study of food reference materials, testing oyster samples, milk powder, fish protein, and lobster samples. These samples were digested and then subsequently analyzed via ICP-OES analysis. In this study, the ETHOS is equipped with the Maxi 24 HP rotor, all controlled by the smart software and infrared contactless temperature. Approximately 0.6 grams of each sample was weighed into the Maxi 24 HP vessels, as reported in Table 1. And trace metal grade acid mixture of 5 ml nitric and 1 ml hydrogen peroxide was used. And you can see the microwave heating program reported in Table 2 here, where we have a 10-minute ramp to 160, a 15-minute ramp up to 200, and then a 10-minute ramp up, 10-minute hold, sorry, at 200. And you can see here on this graph a nice visualization of that heating program that would be trackable during the digestion process with your time in minutes on the bottom and temperature in degrees up the side. We have our 10-minute ramp to 160, our 15-minute ramp up to 200, and then our 10-minute hold. The analytical results can be seen here in the tables 3 to 6 with really good recovery of all the elements, with RSD values being below 3%. What this nicely demonstrates is the robustness and reproducibility of microwave digestion using the ETHOS equipped with the MAXI-24HP, showing successful digestion of a range of food matrices, even highly reactive samples, ensuring superior digestion quality and reliable results. This configuration really provides a complete solution for food testing labs, enabling digestion of a wide range of sample matrices with high sample mass and high throughput simultaneously. As we've seen through the different applications that are suited to the rotor, and in this case study, microwave digestion capabilities support a range of different sectors. And across these sectors, labs often have requirements for diverse and demanding sample preparation processes. The ETHOS can be thought of as a lab station, which incorporates the different sample preparation approaches that are mentioned here on the screen. Taking, say, extraction, for example, this can be used for analysis for microwave-assisted extraction for things such as analytical organic pollutants, PFAS, microplastics, and other environmental contaminants using a specific extraction rotor, all the way to being used for things like determination of fats, FAMEs, and even amino acids in food and feed. Taking this to a slightly different application area, the scope can be extended even further to advanced material studies or geological studies where you need high temperature fusion or fire assays required in the lab using the microwave muffle furnaces. And the system can even be applied to synthetic chemistry workflows using classical glassware, reflux reactions, or even solid state reactors as well. Bringing this back to the food case study, I just wanted to highlight a few target analysis areas that a food lab may be involved in, be that nutrient studies or contaminants. And the ETHOS can really be applied to these different areas. You have the analytes of interest in the middle column on the left-hand side, and then the different sample preparation approaches that the ETHOS can be used for these types of analytes. I've highlighted a couple of application reports that we have available for these different types of preparation. If these are of interest, please do get in contact and we'll be happy to discuss further with you. So moving on from rotor-based digestion, we're going to talk about single reaction chamber microwave digestion. Here we have on the right-hand side, the UltraWave 3, which has been on the market now for a number of years. And then on the left, we have the brand new UltraWave 2 Eco. These systems take all the benefits we've seen of microwave digestion and push them even further by enhancing and simplifying your workflows for elemental analysis. So I'm just going to show you a short video and explain how the system works. So instead of working with the vessels that we talked about for microwave digestion, we use vials with push-on caps. These can be seen here. You have your vials and your push-on caps, a simple two-part system. And these can be made of either Teflon, quartz, or disposable glass, depending on your sample requirements, what elements are of interest, and your acid chemistry. These samples are weighed and loaded into the vials with that appropriate acid chemistry. These are then taken to your analytical system where you are loaded into a PTFE lined stainless steel reactor with a base load. This is then sealed. Once sealed, this is then pressurized with nitrogen. This pressurization with nitrogen prevents boiling of reagents when heated, loss of elements, and prevents sample cross-contamination, all while sealing the caps onto the vials. Once pressurization is complete, the microwave heating program can begin to reach that target temperature that we've set. Using single reactor chamber technology, we can work at much higher temperatures than we could with rotor-based systems. And the pressurization of the system also enables us to work with mixed sample types, masses, and acid chemistries all in a single run. Once the microwave program is complete and we have complete digestion, the system is then assisted cooled. This is either done by water or fan, depending on our model that we have. And then once the system is completely cooled, the system is then vented and pressure is released. Once this is complete, the reactor can be open, our samples can be taken out for final dilution, and analysis can take place. And here you'll just see a nice visualization of our complete digestion of a mix of sample types, acid chemistry, and weights, all in a single run. So as well as having the rapid heating and cooling capabilities of the single reactor chamber microwaves, we've also touched upon the design of the vials and the caps. And what these do is they offer great improvements to efficiency and ease of use in the workflow and really free up a user's time. So I just wanted to go over kind of this operator time workflow for rotor-based technology versus single reactor chamber. So for rotor-based, we have, for both rotor-based and single reactor chamber, the weighing and addition of reagents is the same amount of time. But when it comes to vessel capping and assembly, it takes roughly 25 seconds per vessel to assemble for rotor-based technology, but 2 seconds to put the cap on the vial for the single reactor chamber technology. In the middle here, between capping and venting, we have our microwave heating program. For rotor-based, what we do here is we would take our vessels or our whole rotor back to the fume hood, and we would then tap them or vent them and carry out vessel disassembly. This would take you roughly 25 seconds, whereas with the single reactor chamber, we slightly deviate from the process where the venting takes place inside the microwave system, so no potential exposure to the users, and vessel disassembly is simple removing of the cap. So if we compare that as a whole operator time per sample, for rotor base we're looking at 110 seconds, whereas it's half that for a user when using the single reaction chamber technology. Sorry, bear with me, my slide is not, there we go. Sorry about that. And just for a quick comparison of the two models, as I mentioned, the UltraWave 3 has been on the market for a number of years and is widely adopted across a range of application areas. It really offers you the best performance on the market with working temperatures up to 300 degrees and maximum working pressure up to 199 bar, giving you the ability to digest even the trickiest of samples. This system is water cooled using an external chiller, and in the video represented that was using the UltraWave 3, and you saw the automated reactor opening and closing as well as automated door opening and closing. This system is really applicable to applications with really tough to digest samples, such as geochemistry applications looking to analyze platinum group elements, and things like material testing for lithium-ion batteries, for example. But almost any lab could benefit from single reactor chamber technology, but in the past perhaps didn't need the extreme digestion capabilities that were achievable using the UltraWave 3. This is where the UltraWave 2 Eco comes in and has all those benefits of single reactor chamber technology, with a few adaptations to the model, such as its top working temperature now being up to 250 degrees, but still with that working pressure up to 199 bar. This system is air cooled opposed to water cooled, and also the reactor is manually operated, so manually opening and closing. And what this does is offer labs that improvement to productivity, performance, usability, and safety gain through the single reactor chamber technology at a much more accessible price point. And this makes it an ideal system for labs carrying out environmental testing, food and feed testing, and the pharmaceutical industry. So again, I just wanted to go over a case study because it's always nice to see it applied in the real world. And I'm going to focus on the flexibility of the system. So here, the performance of the single reactor chamber technology was performed doing a recovery study, again, on a range of sample types. We have a lobster sample, a lake sediment sample, and a pharmaceutical sample spiked with a multi-element standard. After the digestion in the single reactor chamber technology, the samples were then analyzed via ICP-OES system. The ultrawave, using the ultrawave overcomes the consideration of sample mass, acid chemistry, and having to run batches required when you're using a rotor-based system. With the ultrawave, you're able to digest a range of sample types, weights, and with differing acid chemistries simultaneously in those simple two-part vials. The pressurization of the system seals those caps on, allowing samples of widely different analyte concentrations to be positioned next to each other in the chamber with no concern of cross-contamination. In this case study, a mix of samples were analyzed, ranging from 0.5 grams up to 2 grams, all prepared for a single run. You can see here in table 1 those range of sample masses and acid chemistries, and a range of vial types run as well. What this is doing is just really nicely demonstrating that one method fits all. And the test described here can be performed on both the Ultrawave 2 Eco and the Ultrawave 3. And here, 8-position rack was used with those mixed vials, but there are a number of different options for rack capacity available for both models of Ultrawave. Table 3 shows the heating program, which is all controlled by a touchscreen. And here we can see there is a 25-minute ramp to 240 degrees and a 10-minute hold at 240. Once our digestion was complete, the samples were diluted up to 50 mils, with deionized water before analysis. Here we can see the analytical results shown on tables 4, 5, and 6, and they demonstrate good recoveries of all elements, and then RSD values below 5%. This demonstrates the robustness and reproducibility of microwave digestion using single reaction chamber technology. And this technology with mixed racks ensures complete digestion, even with different sample masses and chemistry, enhancing the analytical workflow in the lab. The digestion process was accurately controlled by the software, ensuring data quality and reliable results. In addition to this full analyte recovery, using microwave digestion single reactor chamber technology provides the highest level of reproducibility, superior ease of use, and really high productivity for the modern lab. So just to summarize, we've seen how sample prep plays a really important role in the analytical workflow. And then when choosing a technique for this sample prep, there are a number of considerations from a technical point of view. What is your sample type? How much sample do you need to digest? What acid will you need to do? The digestion? And what temperatures and pressures do I need to complete this digestion? And all of these need to be considered when adopting a specific type of digestion. And we've seen how also things like quality, efficiency, costs, and safety play an important role in that decision as well. And we've highlighted throughout the webinar how microwave digestion can significantly reduce those times in sample preparation and also offer really high quality data, all while improving the analytical workflow and the safety to users in the lab. choosing an optimum workflow will really improve the entire analytical workflow for a lab. Thank you for listening. Any questions?
Thank you, Hemi. That was a really well put together presentation. We are knocking at 50 minutes now, so I'll just give a couple of minutes for any questions to come in. But in the meantime, just to let everyone know that our next seminar will be on the 16th of April on pyrolysis. So do tune in to that. And like I said at the start, we will make sure that this webinar is made available to you all to watch on demand.
Thanks, Matt.
Doesn't look like there's many questions, Hemi, so we'll call it a day there. Thanks again, and thank you everyone for watching.
Thank you for attending. Bye-bye.